Okay, and let me pin the video. Come on. Seems a little bit slow, but it's okay. All right. Now let's see how much board I can see. All right. Okay, quadratic functions are represented graphically by shifts and stretches or compressions of the basic squaring function. And that's the definition that I use. Now, quadratic functions are polynomials, so I'll use P of X to stand for a quadratic function. And if we have a series of horizontal shifts and vertical stretches, compressions, and I should probably say up here vertical. It's not really necessary to say vertical stretches and compressions, but I'll include that because it doesn't restrict us. So I'll put in horizontal and vertical here on the shifts. Whether you can read that or not, it doesn't really matter because you understand what it is. And if you have a horizontal shift of f of x equals x squared, well, that horizontal shift is an f of x minus h. If you have a vertical stretch, well, that's going to be an a times f of x minus h. And if you have a vertical shift, that's plus k. And hopefully we're familiar with and understand this. Because if we do, then it's pretty simple. It then follows that P of X. And to keep the notation consistent, I'm going to use a lowercase a here. I usually use an uppercase when I'm doing stretches and compressions of stretches and shifts of a function f of x. But I'm going to use lowercase. If f of x is x squared, x minus 8, f of x minus h is x minus h. Quantity squared. And there is our general quadratic, not our general form of a quadratic function. That's your quadratic function. Okay. It's easy to see from the fact that you're horizontally and vertically shifting the y equals x squared parabola, or a vertically stretched y equals x squared parabola, or compressed, that the vertex is going to be at hk. Because the vertex is originally at 0, 0. If you horizontally shift every point h units in the x direction, the vertex is going to move over to where x equals h. And then if you vertically shift it k units, the vertex is going to move up to hk. Vertex. And vertex starts with a V, not a W. Vertex is at hk. For reasons that are obvious, since the vertex 0, 0 on the x squared graph shifts to hk on any a f of x minus h plus k graph. Okay. Well, that's the first fundamental thing that I want everybody to understand about a quadratic function. Now, we expand A times a quantity x minus h squared plus k. Okay, well, A times x minus h quantity squared plus k equals A times x squared minus 2 hx. Wanted to write xh for some reason. Had to stop and convince myself that that wasn't at all what I wanted to do. Okay. Well, it's equal to this plus k. And that's because x minus h quantity squared is, I'll write this as a little note. It's equal to x minus h times x minus h, which by the distributive law is x times x minus h minus h times x minus h. In other words, x minus h times anything is x times that thing minus h times that thing. Very familiar, hopefully. If not, yeah, worth a review. And then x times x minus h, again by the distributive law, is x squared minus hx. And then this is minus h times x, which is minus hx. And minus h times minus h is plus h squared. And that equals x squared minus 2xh, hx. Plus h squared. So that's why this is equal to this. Now the rest of the simplification is very easy. You get a x squared minus 2ah times x plus h squared plus k. And this is written in the form of a polynomial with the leading coefficient a on x squared. Coefficient of x is negative 2ah. And then your constant term, your coefficient of x to the 0 is h squared plus k.
Professor, shouldn't there be an a in front of h squared?
Yeah, if I understood the distributive law, I would have written it that way, but thank you. And I'm glad you're paying attention because I'm not. Okay, yes. Okay, this is the form ax squared plus bx plus c with b equal to negative 2ah and c equal to ah squared, thank you, plus k. All right. So p of x equal ax squared plus bx plus c is what we call the general form. Of a quadratic function. Now we're interested in the zeros of the function. Okay, what are the zeros of this function? Well, two ways you can find the zeros. A times the quantity x minus h squared plus k is 0 is equivalent to a times x minus h squared equals negative k, which is equivalent to x minus h quantity squared equals negative k over a. And we can see that there's no solution if k over a, if negative k over a is negative. In other words, if k over a is positive, then we have a perfect square equal to a negative number. Okay? So there's no solution if k over a is greater than 0. It's very easy now to see this. Okay? Well, if k over a is less than or equal to 0, then negative k over a is greater than or equal to 0, and we can take its square root. And you can verify that if x minus h is negative the square root of k over a, then when it's squared, x minus h squared is negative k over a. In other words, we square this, we get k over a, We square this, we get K over A. So we have two solutions. Unless K over A is 0, in which case both of these solutions are identical. Okay, two solutions if negative K over A is less than 0. And just one solution if negative K over A is equal to 0. And that solution is repeated. Both of these solutions become the same. Now, what do we mean if negative K over A equals 0? Well, that means that K has to equal 0. Okay, now, so I can say if K equals 0, meaning we have a vertical shift of 0, then we have just one repeated solution. The vertex is on the x-axis. The graph is going to look like this. Because there's no vertical shift, well, the x squared function started off on the x-axis. If your only transformations are vertical stretches, which doesn't change the coordinates of the origin, or horizontal shifts, which just moves the origin along the x-axis, that's what you have. So your graph would look like this, or maybe like this. If your A is negative, that's going to flip everything upside down, but there we have it. Okay. Now, if K is positive and A is positive, then negative K over A is negative, and if negative K over A is negative because of what we've seen here, the square of something can't be negative, so you have no solution. Okay, that's what we concluded already. Graphically, k greater than 0, a greater than 0 means that the graph is upright. The vertical stretch or compression is positive, so you don't have a reflection. So you either have this or maybe you have this. And I'll put an etc. Clearly, you could have your horizontal shift being negative, so this might be on this side of the axis, or this might be on this side of the axis. So there are 4 different ways the graph could look. Okay, this is a positive k and positive a. Actually, I'm getting ahead of myself. So I'm not going to include one that's flipped upside down. We'll take care of that case in a second. So it could be this or this, or could have a vertex on the y-axis as well. And then we can verify easily if k is less than 0, a is less than 0, negative k over r is still negative. And without a lot of explanation, except to wave my hands a little bit, you could have something like this or this. And that's a really bad parabola. That's too sharp. But you get the idea. So if the parabola is totally above the x-axis or totally below the x-axis, well, that means that either k and a have the same, well, k and a have the same sign. Okay, because there are only 2 ways this can happen. So there's kind of an overview of the way the graphs can turn out. Okay, now, analogously, and the algebra is actually a little more complicated for the general form. You're going to get 0 if and only if x equals negative b plus the square root of b squared minus 4ac all divided by 2a, or b minus this square root all divided by 2a. Now I can draw all kinds of parallels between this and the vertex form and what we've learned about this from the vertex form, but we can just kind of regard this independently. It's fairly easy to derive this by a process of what's called completing the square. I'll probably go ahead and talk about that. In some classes, I don't, because it's an important technique. But I kind of leave it to the textbook and the homework to take care of that, even though it probably deserves to be talked about. What this tells you, okay, well, within the quadratic formula, and this is called the quadratic formula, it tells you where the graph intersects the x and the y axis, or I mean, the x axis. Okay, it tells you where the zeros are. Another thing it tells you is that this much of the quadratic formula, well, we got this. I'm going to observe that negative b over 2a is halfway between these zeros. And you can't see the word zeros, so make sure you can. Okay, negative b over 2a, and that b came out kind of small, but I don't want to try to write over it and get sloppier. This is halfway between the two zeros, and that's easy to see because what's halfway between negative b plus something and negative b minus something? Okay, here you're either adding or subtracting the same thing from negative b, meaning that negative b is exactly halfway between what you get if you move this far on one side and move the same distance on the other side. So by the fact that the basic function is symmetric with respect to the y-axis, you find that any shifted and stretched version of that graph is going to be symmetric about a line through its vertex, vertical line through its vertex. So oh boy. I've rebuilt this frame so that I have a nice ledge here, which prevents boards from slipping off, destroying my water bucket, although they haven't heard it yet. But also, if I'm raising my hand, I can, oh, ouch, ouch, easily hit the thing. And you just saw me hit it with this board when I was trying to flip the board. Probably take me a year to get used to this. Okay. And I'll have, much bigger knuckles after this. Okay. Okay, now, what I'm saying here is now, because a consequence of this, our picture looks like this. Our general picture of a parabola we have an axis of symmetry, which is vertical. And through the vertex. This is inherited from the basic squaring function. Through the horizontal shift. Doesn't affect the symmetry about the line through, vertical line through the vertex, and just shifts that line along the x-axis, h units along the x-axis. That also can shift the thing up or down, but the vertex is going to be at on the axis of symmetry. And that is x equals h or x equals negative b over 2a. And of course, negative b over 2a is your horizontal shift. That's your axis of symmetry. And of course, your vertex is hk and that equals h p of h P of h is, and let me check and see if I notated it that way. Yeah, I called this P of x, right? I'm going to make sure that I inherited the notation. P of h is P of x, which is ax squared plus bx plus c evaluated at h, and h is of course negative b over 2a. Now that's a lot of theoretical nonsense, but it should make sense. So I don't know if nonsense can make sense. It might be a contradiction in terms, but that's what we have. Okay, here's an example. P of x, 3x squared minus 12x plus 4. The form is ax squared plus bx plus c, where a is 3, b is negative 12, and c is 4. So p of x is 0 if x equals what? Well, we go back to the quadratic formula, which we can see here. And we plug 3 in for a, negative 12 for b, here and here, and 4 for c, which occurs here. And we get x equals negative b, which is negative of negative 12. B is negative 12. Negative b is negative of negative 12. Plus or minus the square root of b squared, which is quantity negative 12 squared, minus 4ac. So that's minus 4. A is 3. C is 4. And then we divide all that by 2a, which is 2 times 3. Well, we can simplify that. I mean, we can do the arithmetic. We get 12 plus or minus the square root of 144. We square negative 12, we get positive 144. And then 4 times 3 is 12, times 4 is 48. All that divided by 6. And that's 12 plus or minus the square root of 96 divided by 6. And I got carried away with my square root sign there. Want a little bit more room to write the rest of this. By the distributive law, this equals 12 over 6 plus or minus the square root of 96 over 6. Well, that equals 2 plus or minus the square root of 96 over 6. Now, the square root of 96 is approximately 9.8. And it's getting hard to write down here. That says 9.8 over 6. So two plus 9.8 over 6 is about 1.63. And that comes out about 0.37. And that's just fine, except I got hung up on the decimals in the estimate. 2 plus 1.63, I didn't add the 2, is 3.63. And the reason I caught that error is, again, because I know that this and this have to average out to 2. Okay, now, yeah, okay, I've got more space here. So now I know where my zeros are. Then I can say that my vertex we know it's on the axis of symmetry. Which is at x equals negative b over 2a. Well, here's our negative b. Here's our 2a. That's just 2. So there it is. Now, how does this all hang together? And so we still haven't found the vertex. Well, let's go ahead and find the vertex and then see how it all hangs together. Okay. The vertex is on the axis of symmetry. The axis of symmetry is where x equals 2. So we plug in 2 here, and we get the y-coordinate of the axis of symmetry. And this, doing the arithmetic, and there's no advantage to showing the gory details of the arithmetic, we're going to get 12 here, and 4 is 16. Then we've got minus 24. So the vertex occurs at y equals negative 8. So the vertex is at 2, negative 8. And of course, that equals HK. In standard form. So the standard form is, I'm gonna write the P of X in here. This, which equals A times X minus 2 quantity squared. Well, I'll write it plus negative 8. A is the same for the vertex form and the standard form. We saw that, we can see that, except I don't know which board to flip over to see it. Let me see here. Recall, hopefully it's here. No, it's on the back of this board, so I'm not going to show it, and maybe it's behind there. Okay, anyhow, A is the same for the vertex form and the standard form. And if you look back at what I did, you see that it's going to be the same. So A is 2. Plug in the 2 for A, and a plus and negative 8 is just minus 8. There's our standard form. Or the vertex form. Mean the same thing.
Professor, wasn't A 3? Or am I not understanding something?
Yeah, A is 3.
Oh, okay.
I had the 2 in my head.
Okay, gotcha.
Again, thank you.
You're welcome.
A is 3. Okay. I mean, right there it is. And I had the 2 in my brain. And if I check everything, I'll catch that, which is why I always advise checking. Okay. What's this tell us about the graph? Yeah, I don't have the scale to do everything I want, but you can imagine you take the x squared function, you vertically stretch it by factor 3. That's multiplication by 3. Then you shift it over 2 units and down 2 units. Now let's see if that makes sense. Here's the line. Let's see, we want to go up to about 4. So here's the line. X equals 2. Down here at some point is where y equals negative 8. So here's the vertex. 2, negative 8. Here's your vertex. Let's get this board over here a little further, be able to see it better. Okay. The zeros are at approximately 3.63 and 0.37. So let's see, this would be 2, so here'd be 3, here'd be 1. 3.63 is maybe about here. And there's a 0 at that point. And then there's a 0 at 0.37. Well, this is 1, this is 1/2, and 0.37 is more like maybe about here. not negative 0.37, 0.37. And these are approximates. I got to make sure I write it as approximate. Okay. Now, if I put a parabola through here, it'll look something like this. It'll come through here, maybe like so. It'd do that real well. Okay. Now, I did all this without thinking about what the y-intercept ought to be, but there's another thing that we can easily do. The y-intercept is at p of 0. Well, p of 0, we can get it from here if we want, but it's easier to read from the general form. What's p of 0? If we plug in x equals 0, then this term and this term are both 0 because they got multiples of x. So it'll end up with just the plus 4. Okay, so the y-intercept is on the y-axis at y equals 4. So this should be 4. Now that actually turned out quite well. That's 4, then 1, 2 of those gives us 8 units here, and everything is nice and consistent. Okay. Now just a little note over here. Just writing out the details of plugging in 0 into our ax squared plus bx plus c form. Now you notice that the vertex form or standard form and the general form, the ax squared plus bx plus c form, have their advantages depending on what you're looking for. But knowing what the quadratic formula tells us about, and I don't have all the details of that, it's on a different board, but what the quadratic formula tells us about the function, it tells us where it intersects the x-axis. And of course, if this quantity under the square root is negative, it tells us that the graph doesn't intersect the x-axis, meaning it's either all the way above or all the way below the x-axis. It tells us that the vertex occurs when x is equal to this divided by this, or this term right here. There's our axis of symmetry. The vertex is on the axis of symmetry. And by using that, we can easily derive the standard form. Okay, so everything kind of comes full circle here, even though we're talking about a parabola, not a circle. So there we have a whole lot about the graph of a quadratic function. And if we understand all of that and work all the problems in terms of our understanding of this picture, then we get a pretty deep understanding of the graph of a quadratic function. Now, quadratic functions are extraordinarily important. For one thing, polynomials are also quite important. Quadratic function is kind of your, well, linear functions are polynomials, but you know they're very simple. Quadratic functions are polynomials. They're a little less simple than linear functions, but we can pull everything together in this very wonderful picture. Okay, all these interrelationships, the standard form and general form. Where's the vertex? Where's the where are the zeros if they exist. And of course, we can always find the y-intercept. As you work through the section, read the section, you're going to see all this in one way or another. Your book starts with the standard form and then moves toward the vertex form. I started with the vertex form and moved toward the standard form just to complement what the book does. But the result in many ways is the same. Little different way of understanding it. So again, there's the picture. There's something else I wanted to say about it. But I guess I don't remember what that was. And the main thing is to get this picture. Okay, it was another side comment, might well have been distracting, so maybe it's just as well, but I don't make the comment. Okay, now, I didn't think to clean the small boards. I'm gonna take this thing and turn it upside down. What you see upside down here is middle of the semester differential equations. And until you've had a calculus course and some other stuff, you might as well be looking at this upside down. Okay. So we'll just kind of say, okay, this doesn't really exist, but I'll use this part of the board. An example of where you might apply a quadratic function, there are many, many, many examples. This is from economics. In economics, we always sell widgets. So widget is a universal term for whatever it is we're selling. Okay, if we charge X dollars for widget, we will sell No, I don't think well in terms of economics. Math, physics, engineering. I don't know that much about engineering, but I know the math behind it. Yeah, I'm going to say X. We're going to sell 12,000 minus 10X. Okay. Now this is a linear function. And the number we sell, as opposed to the price, isn't going to always be a linear function. But any function, if you look at it closely enough, any smooth graph, if you look at it closely enough, looks pretty much like a straight line. So we're going to use this straight line model, whether you totally understand what I just said or not. At least I said it. Okay, so there's a reason that we start with a linear model. It's the simplest model we can have, and it illustrates some really important things. So if we sell this many widgets, is going to be the number sold times the price per widget. Well, the number sold is 12,000 minus 10x, isn't it? And the price per widget is X. And if we multiply this out, we get this. Okay. If it costs, okay, cost function. Now, I hadn't really thought through this in advance. But let's say our vertex is going to be at 1200. For 1200, we're going to compete with this. If it costs $1,200 or $100 to manufacture and market and sell a widget, okay? Then the profit is P equals revenue minus cost. Revenue is how much money you get, and cost is what it costs to manufacture them. So if you subtract the cost from the revenue, well, you get 12,000x. I want to write this in the standard order. Negative 10x squared plus 12,000x minus 100x. I didn't write this step because I'm running out of room and don't have a good place to write anymore. So we're almost done. But there's our profit function, and we have to subtract $100 for every widget that we sell, which means that our cost is going to be 100x, 100 times the number of widgets. Okay, well, that's a quadratic function. Now, if we apply what I just did, the graph is going to look like this. First of all, the y-intercept is zero. And I really wanted to add some fixed cost to this thing, but you can read about that. To manufacture the thing costs $100 to manufacture a widget, but you've also got to factor in the cost of setting up your factory to produce the things. So there'd be some constant number here, but there isn't one in this example, but that's going to be okay. Okay, you're going to have a graph that looks like this. When X is 0, your profit is 0. Now, I can write this as negative 10x squared plus 11,900x. And now I have 119 divided by 2 is 59.5. That'd be make sure I got my zeros in the right place. 590. And here you have the point 0, 1190. And your parabola having a negative a is flipped over. So you have a parabola that looks like this. And this represents profit versus the number you produce, or versus the cost, I'm sorry. Because X is the price. For a widget. What's our profit? Well, we want to maximize the profit. We want the profit to be as high as possible. So we've just found what our price ought to be. Profit is maximized at the vertex. The vertex is on the axis of symmetry. And the axis of symmetry is very easy to determine. So now we know what our price ought to be. And we just plug 590 into our profit function and we find out what our profit is. Okay, this is kind of a powerful model. And basically we have a linear function here that we multiply by another linear function, simple linear function, just x, to get a quadratic function. Any situation you have where you're multiplying something that's at least temporarily linear by something else that's at least temporarily linear, you get a quadratic, which means it's very easy to maximize it just by doing a graph. Okay. Well, that's what I wanted to share with you today.